Okay, so now I want to talk to you about regularization. We've talked about overfitting, and regularization is a way of modifying or constraining a training procedure to make it less flexible with the goal of avoiding or reducing overfitting, and in so doing, potentially improving generalization performance. So, the idea is that we can make a given procedure, sometimes we can modify it to actually make it effectively less flexible. Okay. So that's one way of thinking about it. And the canonical example, the one I'm going to focus on, is regularized linear regression, because it can help give you the insight what the ideas are. So of course, linear regression, y equals xb plus e. You've seen it before. So the key idea is that you might be fitting this regression based on n observations with p predictors. So you might think of p as being kind of big, and as p gets big, the number of predictors is big, this model can be quite flexible. Maybe it can overfit the data. So we saw an example last lecture. If we increase the degree of the polynomial, which is like adding predictors, how that makes the model more flexible and potentially could actually lead eventually to overfitting of the data. Okay, so that motivates the idea that given a regression, we might somehow want to constrain it or regularize it to make it kind of less predictable. Okay. So what's the simplest way you can think of to constrain the fit? Well, the simplest way I can think of is simply to limit the number of variables that are included in the regression. So if you've got p, say you've got 1,000 variables you've got to choose between that could enter into your regression. If I only let you use one of them, that is, if I assume that although b is a vector with of effects of length p, if I constrain you to only have one non-zero element of b, that is to only use one of the variables, that's like a constrained version of that regression. And in fact, that's called the L0 constraint. So L0 of a vector is just how many, the L0 norm of a vector is just the number, it's written like this, it's just the number of non-zero elements in the vector. Okay, so we could just say, I'm going to constrain the L0 norm of b to be no more than 1 or 2 or 10 or some other value, but constrain it somehow. That would make the model less flexible. Okay, so less kind of hard constraint would be instead to somehow limit the size of those b's, the total size, if you like, of the b effects. So the number of non-zero elements is one way to constrain it, but there are other ways of constraining it. So here's another way. Here is the L2 norm, or the sum of the squared values of b. So that's also a constraint. The idea is if I tell you that that sum of squared values can be no more than something very, very small, in the most extreme case 0, you're forced to set all the b's to 0. But then as I let you have a little bit more wiggle room, you get more flexibility about how to how big b should be. And if I make that constraint relaxed enough, essentially it becomes no constraint whatsoever. So that it goes from a very extreme constraint, the sum of the squared values is 0. That's a very extreme constraint. It says actually all the b's are 0, and you basically have to predict y with 0 in this case. And then the other extreme is to let that constraint be very, very big and say, well, that sum of the squared values must be less than something huge, which is essentially no constraint whatsoever. And you would be back to least squares kind of criteria. Okay, and as I dial that parameter, I get a range of constraints. Same is true if I use the sum of the absolute values. Okay, and these two cases are special enough that they've got special names in the regression context. So using this sum of squared values as a constraint is called ridge regression, and using the sum of absolute values is called lasso, and we'll talk about them both more in a minute. Okay, so that's the idea, is that a way to constrain, regularize a linear regression is to impose some kind of constraint on those coefficients B. Okay, so I've phrased everything in terms of a constraint just because it's kind of easier to think, I think, that way initially by, sorry, I'm a bit dark. So it's easier to think about that way initially because it's clear that you're kind of constraining the fit somehow. But in fact, there's a duality, an exact correspondence between constraining the fit by putting a constraint on the B's and penalizing the fit. So that's these notes here. So C here stands for the constrained problem. So the constrained problem is to minimize some function of B subject to the constraint that G of B is less than some C. And by Lagrangian type arguments, that's equivalent to this penalized problem, that you should minimize the f of B plus some penalty parameter lambda times G of B. So there's here in the first case, the constraint is parameterized by little c. So little c, if little c is small, then it's a very strong constraint. If little c is big, then it becomes a less stringent constraint. In the second case, the constraint is replaced by a penalty. If the penalty's lambda is big, then it's like a strong constraint. And if the penalty is small, if lambda is 0 in the extreme case, then there's no penalty. It's like the unconstrained problem. And so the correspondence between these problems is that if you have for any little c, there's essentially a corresponding lambda. The correspondence might not be that easy to discover, but for any given little c, there's a corresponding lambda. So if you can solve this constrained problem for a little c, it also solves the penalized problem for some lambda. Okay, and usually the way these things work is you don't really know how strongly to constrain it. So that's a dial that you're going to twiddle, or correspondingly, you don't know how much to penalize it. So lambda is going to be a dial. The correspondence doesn't matter too much. In fact, in practice, people usually fit the penalized version. It just ends up being easier to work with, and dialing the lambda, playing with the lambda to regularize the regression rather than working with the constrained version. Okay, so the idea is to fit this penalized regression model. So F is going to be least squares in this case, and G is going to be either the sum of the absolute values of B, or that's the L1 norm, or the sum of the squared values of B, the sum of the squared values of the elements of B. B is a vector, remember. That would be the L2 norm, or you could just have the number of non-zero elements of B. That would be the L0 norm. Okay, so in practice, how hard this computation is for linear regression varies depending on the constraint you choose, or now the way we're thinking of it, maybe depending on the penalty, the form of that penalty function. So if you use the L0 penalty function, that is GB is equal to the number of non-zero elements of B, that leads to a problem P, a penalized problem, that's actually non-convex and computationally very hard. And until recently, at least, it was essentially intractable for modest values of P, and heuristics were usually used to solve it. So the simplest heuristic people would use would be just forward stepwise regression. So let's suppose you had 1,000 predictors, but I told you you're only allowed to use 10, forward stepwise regression would simply start by looking for the best predictor, single predictor among the 1,000. So you just look at them one at a time and see which one reduces the sum of squared, the mean squared error most, and you'd include that one. And then you would take another step in the forward direction, ask, well, given I've included that one, which one should I include next to further reduce the mean squared error to the most, and just keep going forward. So that would not find the global optimum of that problem, but it's a simple heuristic that can at least choose a good set, maybe, or possibly sometimes can choose a good set of 10 predictors. So that's imagine that if you only had 10 predictors and you had the constraint that you're only allowed to use 5 of them, maybe you could look at all subsets of 5 and try every subset and see which one did best, and that would be called all subsets approach. So that's the idea that's the problem you're trying to solve. But if P is not 10 but 1,000, and the constraint is you can use any 50 out of 1,000 or even 10 out of 1,000, it becomes pretty hard work to do that. That said, there are now some integer programming based optimization methods that can solve that problem for pretty big P in minutes or hours. And so yeah, if you're interested in that, you can take a look at this arXiv paper. Okay, so L0 is somewhat computationally intensive, let's say, at least for big P. Turns out that the L1 penalty, the sum of the absolute values of B penalty, that turns out to be lead to a relatively friendly optimization problem. Specifically, it's a convex optimization problem. So convex optimization problems have a unique global optimum, and generally speaking, they're friendly, and you can find great methods to solve them quickly. And in fact, the L1 case, the Lasso case, it's also called Lasso. I think I mentioned that. That's been so well studied, both in theory and in practice, that people have paid a lot of attention to how to do the computation efficiently. And they've, so as I mentioned before, there's this dialing parameter lambda, which is how much of a penalty you put on the, how much you weight the penalty, how much you constrain the regression, how much you regularize. And that's a dial. And in fact, you can solve that P problem, that penalized problem, efficiently, essentially for all values of lambda. So think of it this way. When lambda is 0, you've got kind of at least squares. You've got no penalty. You've got the unconstrained. And when lambda is infinite, infinite penalty, essentially the solution has got to be that B is 0. If you put all the weight on the penalty, then the least squares criteria doesn't matter, and solving that P problem, F here is least squares, G is the sum of the absolute values of B. If lambda is big enough, then that's dominated by G, the sum of the absolute values, and the best you can do there to minimize that is set all the B's to 0. So think about it this way. Think about going from lambda very, very big and then gradually reducing lambda. So as you do that, when lambda is very, very big, all the B's are 0. And then as you reduce lambda, at some point, the optimal will be achieved with one of the B's being non-zero. And as you gradually reduce lambda, more and more B's will become non-zero. And actually, it turns out that it's not obvious, and we'll talk about this again a bit later. It's not obvious, but it turns out that indeed the B's do kind of enter one at a time like that. They don't necessarily enter monotonically in theory, like, they could become non-zero and then go 0 and then become non-zero again. But in practice, actually, they usually go pretty monotonically, but they do tend to enter one at a time. Things change one coordinate at a time. That is, you don't suddenly get 10 coefficients all going non-zero in one go. So that kind of idea has been exploited to essentially solve, this is what's called the solution path. As you vary lambda from very, very big to small, you get a different solution for each value of lambda, and it can find that solution path, that is essentially the solution of B for the, as lambda varies, it in very quickly, very efficiently, almost as fast as solving it for even just one value of lambda. So the solving it for all lambdas is computationally not much more expensive than solving it for just one lambda. In fact, there are some results that say finding it for all lambdas can be quicker than finding it for a single lambda, which might sound counterintuitive. But basically the idea is that sometimes it can be better just to try and compute that whole path than to try and do it just for one particular value of lambda. Okay, we'll see a picture in a moment, but before looking at that, I want to talk about the L2 case. So the L2 case, ridge regression, is also convex, and in fact it has an analytic solution that you can compute provided n and p are not too big. So here it's given here that the optimum B is given by this expression here, where the x prime is x transpose. So x transpose y and is computable, and x transpose x is computable, and you just have to be able to invert this matrix. If P is big, that matrix is pretty big, and that inversion is very expensive. So if P and n are big, you need to use other ways to solve this. But bottom line is that this problem is also computationally very friendly, and in fact analytically tractable for moderate n and p. Okay, so and the GLMNet software in R can deal with the L2 penalty, the L1 penalty, and in fact a sum. You can kind of, a generalization called the elastic net uses a sum of those two penalties. So there are various generalizations. So let's see an example. So again, I like these examples because they do give you the code so you can rerun it yourself. So in this case, the example comes from trying to predict a house price, selling prices based on various coefficients. So like the number of bathrooms, the number of bedrooms, how good the condition is, how many floors, various things, does it have a view, those are the predictors, and it's trying to build a regression model to predict the value, the house selling price. Okay. So what you're seeing here is that on the extreme over here, this is L2 regularization, where you have a very strong penalty. So in a very strong penalty, all the coefficients get set to 0. Sorry, on the y-axis is the value of the B coefficient for each of these predictors. So this extreme right-hand end, that's where there's very strong regularization and everything is getting set to 0. And at the left-hand end here, it's where there's essentially no regularization, or much less regularization. Actually, I'm not quite sure it's got to no regularization, but much less regularization. So the coefficients, certainly if you went to no regularization, you'll get the least squares solution. And you can see, like, as the regularization gets stronger, the penalty gets stronger, the coefficients get smaller and get shrunk. We'll come across this. They get shrunk towards 0. Eventually they get squeezed all the way to 0. We'll come across that terminology again later. So let's see, L2 case here. This is what happens when you plot the same plot for the L1 case. So again, this extreme end here is where everything's set to 0, and then this place where the green coefficient comes out, I can't actually see here, which looks like it's either grade or floors. This coefficient That's it, becomes non-zero, and it keeps getting bigger and bigger until at some point it kind of flattens out to presumably it's close to its least squares solution there. So this is the behavior I was referring to before, whereas we relax the penalty becomes less stringent, and so more and more coefficients become non-zero. So you can see at the end here, well, I know at this point in the solution, we've got maybe 1, 2, 3, 4. Well, these are all zero, I think. 1, 2, 3, 4, 5 non-zero coefficients. And as you go this way, you get more and more non-zero coefficients, although some of them are very, very small here. So it's kind of interesting to see, I think, that essentially any way you draw the line here, you don't get a sparse, in the L2 case, you don't get a sparse solution. Even if I have, this modest amount of regularization over here, there's actually many of the coefficients, probably all of them, well, all of them will be non-zero. Whereas under the L1 case, it tends to give you sparse solutions. Okay, so as you penalize this, here only one of the coefficients has non-zero. And there's a good reason for this, and we'll come back to that in a minute. But that's one reason that people often prefer the L1 regularization to the L2 regularization, because they like this fact that it gives you sparse solutions, which tend to be maybe a bit more interpretable because they only involve a small number of the coefficient, small number of coefficients, small number of predictors. Makes it a bit easier to interpret the results. And in some cases, it might also provide more accurate predictions, but it doesn't have to. I should say in this case, I think they compare the prediction error using L2 and L1. And actually, so you can see that this is the test error. You can see that the test error for the L2 is minimized somewhere over here. And the test error for the L1 is minimized somewhere over here. So you can see that, again, you can see this idea, whereas the regularization gets stronger. At first, the error gets, this is no regularization. The error gets better and better and better. That's a test error. And then at some point, the test error starts to get worse again. Of course, the training error is always going to get better because as you relax the penalty, relax the constraint, is not as constrained. The old solutions are still going to satisfy the constraint. If you think about it in terms of the constrained way, it's easier to think about it like that. If you relax the constraint, the old optimum is still going to satisfy this constraint. So you're always going to be getting a better and better optimum as you relax that constraint.